Hi, and welcome to this section of the Physics 3 tutor, and in this section we're going to continue talking about capacitors. In this section we're going to start to talk about energy storage in a capacitor, which is really sort of the whole point of having capacitors in circuits anyway. So we've talked about how to calculate capacitors in series and parallel and gotten some experience with the theoretical basis of what a capacitor is. And now we're going to start to talk about how many joules are actually stored in a capacitor. Which is, a very useful thing to be able to calculate. I want you to recall from earlier sections that just basic electric theory, when we have an electric field present in this room, which by the way we do all the time, then that electric field has the potential to do work on a charged particle. If we have an electric field here, I could draw some arrows on the board. For instance, if we put a proton or an electron just sitting out there in free space and we let go of it, then that electric field is going to begin to move and a Coulomb force is going to appear and push that electron or that proton along according to Newton's laws, F equals ma. But that force is going to pop up, and that force is going to be what we call the electrostatic force, and it just is because that electric field and that particle are in basically the same location. So when you boil it all down, that electric field has the potential to do work on that charged particle, just like this gravitational field has the potential to do work when I'm holding an apple up here. As soon as I let it go, it begins to move. So that gravitational field begins to convert that potential energy into kinetic energy. So if I'm holding a proton there, I have potential energy as well. If I let it go, it's going to begin to move. So the electric field, when it's present, it does sort of contain and sort of represent energy that's there. The potential to do work is potential energy. So the fact that the field is there at all means that there's potential energy there. Or if you want to shorten it, you could just say there's energy there because the electric field. So electric fields have energy. We're going to learn later magnetic fields are also going to have energy. And when you combine them into an electromagnetic wave that travels, that wave is going to carry energy, from me to you or from the sun to the earth. So it's sort of the nice circle of life there. Everything has energy in relation to electricity and magnetism. So when we talk about the fact that an electric field has energy associated with it, potential energy, and we've also already said that inside of a capacitor with these two charged plates, there's an electric field in there. Then it stands to reason if there's an electric field inside that capacitor, which there is, then that capacitor contains energy or is storing energy. And that's kind of what we say in the beginning of the course. Capacitors are sort of like temporary batteries. They can sort of hold a charge and they can deliver charge whenever they need to. And that's coming from the energy stored in that capacitor to push those charges out when you connect that capacitor to a circuit. So that's sort of the general fluffy thought of why capacitors might contain energy. Now let's get into some of the math and figure out what it really is. Now let's draw a quick little picture just to remind you. You have a parallel plate capacitor. So here's one plate and here's the other plate. And over on this side, maybe you've got your positive charges. So this charge on this plate is positive Q. And then over here, maybe you have your negative charges because they always have to be equal and opposite. So this will be negative Q over here. That's just what we talked about in terms of a capacitor. So if that's the case, then what's the electric field going to look like in here? Well, it's going to go from positive to negative like this. So this is the electric field inside here. So I'm going to put like an E with a bar on top. That means it's a vector electric field there. So the electric field does exist between the plates. And we've already sort of talked with a little thought experiment. We know that if we put a charged particle in here, it's going to move. Therefore, this field must have potential energy, the potential to do work on something. So it does contain energy. So if we take this capacitor, which has this electric field, and we have stored this charge on it like that, and if I go over here and connect this capacitor to a circuit, which might have all kinds of things down here, resistors, transistors, all things down here, and I connect it, what's going to happen? Well, these stored charges that are on the plates are going to begin to move out into the circuit. Now, what is the energy stored inside this capacitor? So without any proof, I'm going to tell you, I'm going to give you sort of a little proof in a second, but the potential energy stored in a capacitor is, and I'm just going to sort of put it here. We usually talk about U to represent potential energy. So we'll do the same thing here. It's Q squared, so the value of the charge stored in there squared, divided by 2 times the capacitance, and that is going to give you a number in joules, nice friendly unit of energy. This is exactly the same thing, or equivalently, U can also be rewritten as 1/2 times the capacitance times the voltage across that capacitor squared. This is the voltage across the capacitor. The reason, so let me go ahead and kind of box this. This is the main formula of this entire section. There really aren't too many more formulas here, or equations. The reason why these are equivalent, it's nothing magical. It's just that, don't forget, Q is equal to CV. That's just the general thing, the general relation of the capacitor. So if I take this and I go ahead and substitute in there for Q, then what I'll have on the top is C squared V squared, if I put this in here, and on the bottom I'll have 2C. So you see, this guy is going to cancel with this, so what you'll have is CV squared times 1/2, which is really what you have. So the reason we present both of them is because in some problems you may not know what the voltage is across the capacitor. In that case, you might know the charge and the capacitance, so you'd use this guy. And over here, you might, you might know the voltage, and so you would use that guy. So that's sort of without any proof. That's what we have here. Now, what I want to go and tell you something else here is really interesting and important. I'm going to sort of connect the dots a little bit here. At any point in space where the electric field E exists, which is pretty much everywhere, by the way, the energy density is and by the way, don't let words like energy density scare you. I'll explain a little bit in a second what we mean by that, but it's not a hard thing to understand. The energy in free space, if an electric field is just present, is equal to 1/2 times the permittivity of free space, epsilon naught, times the electric field squared. And the units here are not going to be in the unit of joules because this is an energy density. So it's going to be joules per cubic meter. Joules per cubic meter. So what I'm trying to say here is I'm just giving you, I'm kind of, fire hose in your face with a bunch of different equations, and you're sort of going to have to believe me here a little bit. But basically, this can be derived from this. This is the energy stored specifically inside of a capacitor, and we'll derive it here in a second for it. The more general equation is this one. This one basically says that I don't care if I'm in a capacitor or if I'm inside of a railroad car or if I'm inside of a spaceship or if I'm in Earth orbit or whatever. If there's an electric field there, then all I got to do is square it, multiply by that constant, which is permittivity of free space, and then multiply by 1/2, and I'm going to get a number. And that's going to be how many joules exist in every cubic meter of space where that field is present at that strength. So when you say things like energy density, it sounds really sci-fi and really, out there, but it's not, because when you think about the term of density, regular density, I'm talking about density from chemistry 1 or physics 1, I could easily call that mass density. And you might say, whoa, what's mass density? Well, it's just regular density. It's kilograms per cubic meter. How many kilograms of mass do I have for every cubic meter of space? Well, this is an energy density. It just means how many joules do I have? If I take a box and measure 1 meter by 1 meter by 1 meter and I get a box, how many joules exist inside that box? Because this electric field is present inside of it. So that's why it's an energy density. The reason it's an energy density is because this is the way that it was derived to give us this expression here. So I didn't prove this to you. This is just something that you're going to have to accept. It's proven and really demonstrated by experiment more than anything else. Now it turns out that these equations do sort of follow from this one. So I do want to show you that real quick because you're very likely to have to show that on a test. So let's see if we can figure out how we can derive these guys from the more general relation, which just talks about the electric field. So what we're going to have is, if we take a parallel plate capacitor, which is what we usually always talk about. A parallel plate capacitor has a plate like this, and there's another plate maybe like that or something like that. And the area of this plate is A, and the distance between these plates is d. The distance between those plates is d. And so, just recalling a few formulas, the electric field inside of this parallel plate capacitor is V over D. The voltage applied across the plates divided by the distance between the plates. So the electric field is going to be higher if I put a higher voltage across it. The electric field is going to be higher if I make the plates really close together by making D very small. And this is for a perfect capacitor with big plates and all that stuff. Now don't also forget that the capacitance of the perfect parallel plate capacitor is epsilon naught times the surface area divided by the distance. So same sort of thing. The capacitance gets bigger if the area gets bigger. Capacitor gets bigger if the distance gets smaller as they get closer and closer together. So if I want to think about everything that I've sort of learned here, here I have an energy density. If I have an electric field anywhere, this is the energy density. So the total energy stored in this capacitor is going to be equal to the energy density times the volume of space that I have. In other words, if I want to talk about units, which I love talking about units, you can learn so much about units. The energy density is how many joules exist in every cubic meter of space. Well, if I take that and I multiply by however large my space is, then meters will cancel with meters and I'll be left with joules. That will be the total energy stored. So let's see if we can apply it in exactly that way and get somewhere. So we'll say equals, what is the energy density? Well, it was given to us right here, 1/2 epsilon naught times E squared. So that's going to be 1/2 epsilon naught times the electric field squared. So that's the first term here. This is the energy density. Now what's the volume of space I have? Well, if I'm looking in a parallel plate capacitor, then the actual electric field only exists in between the plates. So the volume of space that contains this electric field is going to be, don't forget, this is D here, the distance between the plates. If I know the surface area of the plate here and multiply by this distance here, then I'm going to get the volume of the inside of that capacitor there. So what I want to do is take the surface area of this plate, multiply it by the distance between the plates. That's going to be the volume of this little interior region between the plates. So here I have the energy density joules per cubic meter times the volume in cubic meters. So I should get joules as an answer. Okay? So that's basically correct. What we want to do next is 1/2 epsilon naught. We want to do a substitution because I know the electric field for this particular arrangement of a parallel plate capacitor, and it's V over D. So I'm just going to substitute that in there. And then I'm going to be multiplying by A and then times D. So what we're going to get next is, let's go ahead and continue simplifying. 1/2 epsilon naught V squared over D squared times A times D. Well, now we're starting to get somewhere because D will cancel with this guy right here. And then here I'm going to do a little bit of magic and I'm going to say, all right, let's take A and let's move him over here. 1/2 epsilon naught A over D times V squared. I just moved it over here. I didn't do anything else. Now this term right here is equal to 1/2, it's going to be equal to this guy right here. So I take this away. This part of the term, epsilon naught A over D, is equal to the capacitance of the capacitor that I've drawn there. So what I have here is 1/2 C times the V squared, the voltage squared. And this is the energy stored in this capacitor, which is exactly what we said it would be equal to here, 1/2 CV squared. So you see, the more general equation is this one. This is the energy storage. It doesn't matter what you're talking about. Capacitor, inside of a box, anything. If I have an electric field somewhere, if I know what the strength is, this is going to tell me how many joules per cubic meter exist where that field is. All we did was take that, and knowing the arrangement of the capacitor, we plugged in the volume of the interior region, and we used what we knew what the field strength was of a capacitor to manipulate it and show us what the actual electric field is inside of a capacitor in terms of things we usually know, because we usually know what the capacitance is, we usually know what the voltage is in a circuit, so we can calculate how many joules are stored in a capacitor. And as you might guess, as we increase the capacitance while holding everything else constant, the energy goes up. as we increase the voltage on the capacitor, holding everything else constant, the energy goes up. All right, and I put E here, but this is equal to U, the potential energy. So that's just to make sure it's clear. I used E here because I'm used to using E for energy, but this is really the potential energy stored here. So we have enough information to begin to solve a few problems, and you're going to find that they're not that difficult. You just need to understand what the definitions are and go from there. So the first one is a parallel plate capacitor has a value of 130 picofarads. If we apply 56 volts to the terminals, how much energy does the capacitor store? So you need to use one of these equations that deal with energy storage. First one that comes to mind, 1/2 CV squared. And it tells us in the problem, it's 150 picofarads. So it's going to be 150, but you can't use picofarads, PF. You have to put it out in terms of farads, times 10 to the minus 12, because that's pico. And it's 56 volts, so 56, and we're going to square that because V squared. And when you do all this stuff, you get 2.04 times 10 to the minus 7. 2.04 times 10 to the minus 7, and that's joules. All right, 2.04 times 10 to the minus 7 joules, which is exactly equivalent, if you want to put it in terms of microjoules or something, to move it over here, 0.204 microjoules. You can leave it like this in terms of joules if you want, but some people like to use the metric prefixes. In order to use micro, you're going to have to move that decimal up, though, because you know, there is no metric prefix for 10 to the minus 7. All right. The next problem is kind of interesting. And basically, it goes like this. It says we have two capacitors. One of them is 2 microfarads, and the other one's 4 microfarads. We connect them in parallel across a 300-volt source battery. What is the total energy stored in the capacitors? The total energy stored in the capacitors. So we have to use a little bit of knowledge of circuits combined with the knowledge of capacitors to figure that out. So what we have is some kind of source that's 300 volts. You could put a battery symbol there if you want. I'm just going to put 300 volts there. And we have one capacitor. It tells us they're in parallel. So I'm going to put 2 capacitors basically in parallel. This guy is 2 microfarads, and this one is 4 microfarads. And the question is, what's the total energy stored in the capacitor? Well, what you need to realize first out of the gate is that whenever you have anything, capacitors, or later on we talk about resistors or anything, if they're directly in parallel with this battery, then the voltage across this capacitor is 300 volts, and the voltage across this capacitor is also 300 volts, because they're directly connected in parallel to that battery. You have to know that. That's really the only trick to solving this problem. So, in a capacitor in general is 1/2 CV squared. So see, we would use this form because we know the capacitance and we know the voltage. All right, and since we know the voltage across both, it's going to be 1/2. This guy, capacitance, is 2 times 10 to the negative 6. The voltage across this guy is 300 volts squared. So that's the energy in this guy plus the energy stored in this guy. 1/2, 4 times 10 to the minus 6 times 300 squared. It's also 300 volts because it's connected directly to the battery. That's really the only trick. If you didn't understand circuits at all, you wouldn't know what voltage to put there. You wouldn't be quite sure. So now that we have this, you just literally plug this in your calculator and you'll get 0.09 plus, you put that in your calculator, you'll get 0.18. So when you add them both together, you'll get 0.27 joules. That's how much energy in joules is stored in there. Now there's more than one way to do a problem. If you wanted to do it differently, you could combine these capacitors into an equivalent capacitance, like we learned how to do a couple sections ago. And then you could use that equivalent capacitors, like one big capacitor there, and then do 1/2 CV squared using the equivalent capacitance. But you know, I think you can kind of see you're going to get the same answer, because if we add these, because in capacitors in parallel, we just add the values of the capacitance. So we would get 6 microfarads for that new capacitance. So we would have 1/2 times 6 microfarads times 300 squared, and we would get the same thing, because we're just breaking it out here, adding it up a little bit separately, but it's really exactly the same thing. So there's more than one way to do a problem, you know, but in this case I chose to add them up individually, mostly so you can see see how things are added together and how the circuit's really working. Okay, the next problem says a capacitor is charged by a potential difference voltage V. We don't know what it is. If you want to increase the stored energy in the capacitor by 10%, what percentage do you need to increase the voltage V? Seems like a really simple problem, you know? What you have is a simple circuit, voltage connected to a capacitance. You want to increase the stored energy by 10%. How much should you increase the voltage? You might think it's 10%, but it's not because of the following thing. Let's talk about why first. What we basically have is some voltage connected to capacitance, C. And we want to increase it by 10%, but don't forget, the energy stored in a capacitor is 1/2 CV squared. So if we increase the voltage 2 times, then the energy increases 4 times. So it's not a simple one-to-one thing. You can't just increase the voltage 10% and expect to get 10% energy storage. It's not gonna work out that way. So the way to attack this is you really need to realize this is the energy stored in the capacitor, and you need to really read the problem to see what you need to do. You want to increase that voltage increase that energy stored in this capacitor by 10%. So in the end, when you're done, you want to have the energy stored in that capacitor plus 0.1 times U, because that would be increasing it by 10%. You would have the energy you had to begin with plus 0.1 of that, this is the 10%. You're increasing it by the 10%. Equals. This is the new energy that I want stored in this capacitor, 1/2 C. And the question is, how much do I increase the voltage V? So I'm going to have my initial voltage and I'm going to increase it by something. I don't know what it is. I'm going to call it P for percentage, V squared. This is the master equation. This is what you need to make sure you understand, because the rest of it's just algebra. But this is usually the very first step in a physics problem, is what really is the hardest. So what we read into the problem is we want to increase the energy by 10%. So we have energy plus 10% of the energy equal to 1/2 C V squared. But we don't know how much we need to increase that voltage, so we call it P, because we don't know. We're going to solve for P, and it's going to be a decimal, and we're going to be able to tell the percentage. So what we want to do next on the right-hand side is say 1/2 C. In here, let's go ahead and factor out a V, 1 plus P squared. So we just factored out a V in there. And the reason we want to do that is U plus 0.1 U. Ultimately, we want to basically solve the equation for P. So we're just going to try to do as many things as we can to get in that general direction. So what we're going to have next inside the brackets is V squared, because you got a square term here, times 1 plus P squared. Now we get rid of the square on the outside. So we just basically used our algebra to take this square and apply it here and also into there. All right? So we're in pretty good shape. These brackets really don't mean anything. We just sort of left them there. At this point, the only way we're going to make any progress is to begin to use what we know about capacitance. The energy stored in a capacitor is equal to this. So let's take this and substitute it in, because if we do that, we'll have an equation in terms of V, and we'll get rid of this U, and we'll have a better shot at going here. You don't really know at this point if this is going to be the correct thing to do, but what you do know is that it's legal, because you get to this point, this is the energy. All I'm doing is taking the energy and putting it in there. Let's see where it takes us. So what we're going to have here, this is 1.1. If you have U plus 0.1 U, it's 1.1 U. So 1.1 U, but U is equal to this, 1/2 CV squared, equal to 1/2 CV squared, 1 plus P squared. So now you see why this was useful, because this 1/2 CV squared cancels with this 1/2 CV squared. And that's the only reason why it made sense to do that. Of course, you don't see that ahead of time a lot. So 1.1 times, or equal to, and you have 1 plus P squared, right? And so we want to solve for the percentage, so we're going to take the square root of both sides. So 1 plus P is equal to, let's take the square root of 1.1, you're going to get 1.049, and that's taking the square root of both sides. P is going to equal to 0.049, which means moving the decimal point, 4.9%. 4.9%. We're going to increase it by 4.9%. So if we want to increase the potential energy in that capacitor by 10%, we have to increase the energy, the voltage on the terminals of that capacitor by 4.9%. And again, we wrote the equation, we understood that it was right, we plugged this in on a hunch, and then it became clear that this was going to cancel. I don't know who you are, but ahead of time, you're not going to know that this cancellation is going to happen. You're just not. Unless you're really, really good at this stuff ahead of time. Usually when you're doing these problems, you write down the equation you know to be true, write down any other constraint equations, because we knew it was a capacitor, so we knew that applied if you know it to be true. Try substitutions, try different things, trying to eliminate variables. In this case, I knew if I put U in here, I would get rid of U at a minimum, and maybe something magical would happen. But you don't usually see that until you really get into it. So, biggest problem with physics is people try to solve the problem in their head. They try to figure out how they're going to map their way to the finish line, and they just need to write the steps down. You can't do that. You really cannot do that. And this problem was relatively easy, really, not too many steps. If you have a page of work, you're never going to be able to do that in your head. So don't even try. Just try to write things down that are legal and make sense. All right. The next problem says, a parallel bank of 2,000 capacitors, 5 microfarads is each one of these capacitors, stores energy. If the power costs 3 cents per kilowatt hour, how much does it cost to charge the bank up to 50,000 volts? So we have a large circuit of capacitors, something like this. We have 2,000 of these. So I'm not going to draw 2,000 of them, but basically you get the idea. They're all in parallel. And so we want to figure out how much money it costs to charge it up to 50,000 volts. So the first thing you're going to see, if these are all in parallel, the equivalent capacitance is just basically going to take 2,000 and multiply by 5 microfarads, because each one of these is 5 microfarads. 5 microfarads. So the equivalent capacitance is 0.01 farad. If you take 5 times 10 to the minus 6, multiply by 2,000, you're going to get 0.01. And that's in terms of farads. The reason it's such a large number is because you had 2,000 capacitors and you add them together like that. All right? So we know now that the circuit has an equivalent capacitance associated with it. We want to charge it to 50,000 volts. So we'll charge to 50,000 volts. So where do we get? U is equal to 1/2 CV squared. There's 1/2. The capacitance is just simply 0.01. The voltage is 50,000 volts. 50,000 volts. Don't forget to square it. So the potential energy stored in this bank of capacitors, if we do this multiplication right here, is going to equal 1.25 times 10 to the 7 joules energy stored. In other words, that's a lot of energy. That's a lot of energy. That's over a megajoule of energy stored in all that capacitor. So that's a lot of energy. So the question is not, I circled it really, that's not the final answer. The question is not how much energy is stored, because that's pretty easy. The question is, how much money does it cost to store this power or this energy in the bank of capacitors if the power cost, and we say 3 cents per kilowatt hour. Now, we need to talk a little bit about kilowatt hours. It's a pretty practical thing because all the power that goes into your house is measured in terms of kilowatt hours. A kilowatt hour means that 1 kilowatt, which is 1,000 watts, 1 kilowatt is delivered to your house for 1 hour. That's what it means. So, a watt is a joule per second. So that's what a unit of power is. The electric company deals in terms of power, but we deal with it in terms of how much, if we had 1,000 watts delivered to your house for an entire hour, right, then that would be the unit of sort of energy that we measure coming from the power company. And that's how they use to price it, because the more you consume the energy, the longer you consume the energy, the more you're charged. So instead of dealing in terms of joules of energy delivered to your house, they deal in terms of kilowatt hours. So how 1,000 watts delivered to your house for 1 hour. 3 cents for every single block of an hour that comes in with 1,000 watts. There's a lot of ways to proceed here. You want to basically know how much it's going to cost to deliver this many joules, but notice joules really isn't anywhere in this thing in terms of the power cost, but if you think about it, it is, because the unit of watt, a watt is a joule per second. A watt is a joule per second. So joules is really wrapped up inside of this unit there. So there are a lot of ways to proceed. This is the way I'm going to proceed because I like to do my unit conversions in a certain way. So what I'm going to write down is 3 cents per kilowatt hour. That's how you write that, 3 cents per kilowatt hour. All right. And what I'm going to do is write it in terms of a unit conversion. 3 cents per 1,000 joules per second. And let me write this down, hours right here. You'll see where I'm going with this in a second. A kilowatt is a kilojoule per second, or 1,000 joules per second. So it's on the bottom here. So inside of this unit is basically joules per, or thousands of joules per second. So I have 1,000 for the kilo, and then joule per second. Now it's got to be written with the joule on the bottom and the second on the top because we're in the denominator. So you know, on the bottom here we really have joules per second. So in order to write it as a unit conversion, I got to kind of flip it over and write it like that. Hours just stays on the bottom because the hours is always there. Okay? Now what I need to do now is try to convert this into something that makes sense. So let me go ahead and change colors here a little bit. Let's say that 1 minute is 60 seconds. That's going to cancel seconds with seconds. And let's say that 1 hour is 60 minutes. And what we're going to get there is minutes is going to cancel with minutes, and hours is going to cancel with hours. So you might say, why did you do all that? Well, if I do this multiplication here, 3 divided by 1,000 divided by 60 divided by 60, what I'm going to get in the end is, let me erase this. When we do that, is we'll get 8.3 times 10 to the minus 7 cents, because don't forget cents are still on the top, cents per joule, because joule is still on the bottom. That's really what I want to know. I want to know how many cents per joule is this power going to cost me. And in this case, it's costing me this much power, or this much money per every joule delivered. Because if the power company actually measured your bill in terms of cents per joule, then this problem would be easy, because all you got to do is take the number of joules you have, multiply by this number, and to get the number of cents it's going to cost you. And that's what we're going to do to solve the problem. But the power company doesn't do it that way. That's exactly what this unit is equivalent to, but people are used to thinking of watts and things like that, so they're not going to know what a joule is. So the power company always delivers it in terms of kilowatt hours, also because the amount of energy a house consumes is very large. So if you started talking about it in terms of joules, then it's going to get to be such a large number. So we talk about kilowatt hours. But basically we take kilowatt hour by breaking it into joules per second, hour stays at the bottom, and then we convert all the time so all the time disappears from it, so what we're left with is joules per second. Now if we take this guy, 1.25 times 10 to the 7, which is how many joules I have stored inside of that capacitor bank, and I multiply that by 8.3 times 10 to the minus 7, this is cents per joule, then you can see from the units that this joule is going to cancel with this joule, and I'm going to be left with cents. And so at the end of the day, when I do that, I'm going to get 10.4 cents. And that's the answer, 10.4 cents. Not a big deal. The hardest part of this problem was understanding what a kilowatt hour was. And knowing how to work with that. It's a little bit cumbersome, I'm going to be honest with you, because you've got money in there, and it's not watts, it's kilowatts, so you have to make sure you have your 1,000 in there. But that's why it's a good thing to know how to do. All right. Final problem says, we have this electric circuit, I'm going to draw it on the board. We want to find the charge, the potential difference across the capacitor, and the energy stored in each one of these capacitors that I'm about to draw in this circuit. So we have a circuit here like this. There's a voltage between the terminals. We don't, actually we do know what it is. It's 100 volts. All right, and then over here we have two capacitors these are in series here in this branch, and then we have another capacitor over off by itself. This third one, C sub 3, is 4 microfarads. C sub 1 is 10 microfarads, and C sub 2 is 5 microfarads. So this is the circuit. It's a simple looking circuit, but you do have one leg here with 2 capacitors and then another leg with a single capacitor. And we want to know the charge, the potential difference across each of those capacitors, and the energy stored. So what we want to do first is let's work on the charge in each one of these capacitors. One thing you need to sort of think about before you do any math is learn or remember back to what we learned. When we have this leg of this capacitor and the leg of this capacitor here, these two capacitors are in series with one another. Yeah, they're in another parallel leg of the entire circuit, but inside of this leg, these are in series with one another. And when capacitors are in series with one another, we talked about, they are always going to contain the same amount of electric charge when they're in series with one another. If you don't remember that, go back to the first section on capacitors. We talked about that in great detail. So knowing that fact, what we're going to have here, when you sort of think about it, is there's going to be a voltage across this capacitor, you know, between this point and this point here, and then there's going to be a voltage across this capacitor, V sub 2, and they're going to be different. The voltages are going to be different, but the electric charge stored in each one is going to be the same. So if I use that fact, then what I'm going to see is V1 plus V2, this voltage here plus this one here, is going to equal the 100 volts that's across the whole thing, because that's basically here. So V1 plus V2 is going to equal 100, and that's going to equal, don't forget one more thing I need to write, in terms of capacitor, since Q is equal to CV, then V is going to equal to Q over C. The voltage is equal to the charge on the capacitor divided by the capacitance. So V1, which is this guy here, is going to equal Q over C1. Plus V sub 2 is going to equal Q over C sub 2. I left Q alone. I didn't put any numbers on it because the charge stored here and the charge stored here is actually the same. And that's what I'm doing. If I put Q1 and Q2, then they would be sort of different values and they wouldn't be able to do anything. But since I know that these are in series right here, I know they're going to have the same amount of charge on there. The voltages will be different because I'm splitting this parent voltage up across like that, but the electric charge will be the same in there. So what I'm going to basically do next is I'm going to say 100 is equal to, let me factor out the Q, I'm going to have 1 over C1 plus 1 over C2. All right? And so Q is going to be out here. C1 is known, is 10 microfarads, 10 times 10 to the minus 6. C2 is known, that's 5 times 10 to the minus 6. And there you go. All I really need to solve for is Q, and that's easily done. So what I'll have is 100 is equal to Q, and inside of here, when you take 1 over this plus 1 over this, you're going to get 300,000. So then I can solve for Q just by division here, and I will get 3.33 times 10 to the negative 4 coulombs. 3.33 times 10 to the minus 4 coulombs, which is exactly the same thing as 0.33 millicoulombs, moving the decimal one spot to the left so I can use the prefix milli. So what this means, and another way of saying it, is Q1 is equal to Q2, which is equal to 0.33 millicoulombs. And that was really the answer to the first thing. Again, really the most important thing with this part of the problem is knowing that the charge is the same in here and here. If you didn't remember that, you wouldn't be able to solve the problem because it's a crucial thing to know. The other thing to know is that the voltage across this capacitor plus the voltage across this capacitor must equal the total voltage across the whole thing. And that's also something that I'm hoping to give you the experience with circuits so that you'll intuitively understand. It doesn't really matter if this is a resistor or capacitor, or inductor, or whatever. The voltage drop across everything in this leg has got to equal this because this is what's physically across that leg. Okay, let's go ahead and do the next part. And the next part says, let's go ahead and find the voltage drop across each one of those capacitors. Actually, what I want to do now is go ahead and erase this over here so that I can still refer back to my circuit. Okay, so what we've got is we know that Q is equal to CV. So what we want to find is the voltage drops everywhere. So V is equal to Q over C. Now we know what Q is here for these two capacitors. We just calculated that. And actually, I'm just noticing we didn't even calculate the Q for the third one over here. So let's do that right now. That's actually even easier. That's the easiest part of the problem. For this guy over here, Q is going to be equal to capacitance times voltage. This voltage is across this leg, and it's also across this leg. So Q3 is equal to C3 times the voltage across 3. So C3 is 4 microfarads, 4 times 10 to the minus 6. V3 is 100. 100 is across this leg as well. So 100, just like that, CV. And so when you multiply these things together, Q3 is equal to 0.0004 coulombs, which is equal to 0.4 millicoulombs. 0.4 millicoulombs, and that's what that's equal to. So we found Q1, Q2, and Q3, which is what part A was. Part B is let's find the voltage across them all, but that's just using the same relation right here. So what we're going to have is V1 is equal to Q1 divided by C1. Q1, 0.33 millicoulombs. Of course, we want to do it in its full glory, so 3.33 times 10 to the minus 4 coulombs, divided by C1 is 10 times 10 to the minus 6, because it's 10 microfarads, capacitor number 1. So V1 is equal to, when you do that division, 33 volts. All right, now let's do the same thing for V2. V2 is equal to Q2 over C2. Q2 is exactly the same as Q1. That's what we found. Those charges are the same in that leg right there. So we've got 3.33 times 10 to the minus 4. And capacitor number 2 is 5 microfarads. And so when you do this, V2, when you do that division, you're going to get 67 volts. So let me start circling. That's that one. And then for V3, you're going to have V3 is equal to Q3 over C3. Q3 we just calculated, 0.0004 coulombs, 0.0004, divided by the capacitance C3, which is 4 microfarads, minus 6. And then when you do that division, V3, 0.0004 divided by 4 times 10 to the minus 6, you're going to get 100 volts. Now I want to stop here to make sure. Let me circle this, let me circle this, and let me circle this. Make sure that you really understand this, because everything's self-consistent. What we found is the voltage across capacitor 3 is 100 volts, which is exactly what we said it should be because it's connected across the terminals like that. All right, what we said over here is that V1 is 33 and V2 is 67. V1 is 33 volts, V2 is 67 volts. But if you add up 33 and 67, this voltage plus this voltage, you'll get 100, which is exactly what is across both terminals. So everything's self-consistent. Okay. Third one is, what is the energy stored in each of these capacitors? So it's just going down the line. U1 is equal to 1/2 C1 V1 squared. What's that equal to? 1/2 C1 is 10 microfarads. V1, we just calculated 33 volts squared. And so U1, 1/2 times that squared, we'll get 0.0054 joules stored in this guy, which is the same thing as 5.4 millijoules. Because if we put the decimal here, it'd be 123. That would be milli. So let me go ahead and circle this as an answer. U2 is going to equal 1/2 capacitor 2, voltage 2 squared. Whatever this capacitance is, whatever this voltage is. 1/2 Capacitor 2 is 5 microfarads. Voltage 2 is calculated here, 67 volts, square it. So U2 is equal to, when we do all that multiplication, we will get 0.0109 joules, which is equal to 10.9 millijoules. The reason it's 10.9, if we move the decimal here, that would be 123, giving us millijoules. Again, you can leave it in terms of joules, that's fine. It's just a lot of people like to use the metric prefixes, but you got to move your decimal point to the right place to do that. Finally, U3 is equal to 1/2 C3 V3 squared. So 1/2 C3, capacitor 3, is equal to 4 microfarads. Voltage 3, we calculated as 100 volts squared. And when you do that math, you'll get U3 is equal to 0.02 joules, which is 20 millijoules. 20 millijoules. And again, 1, 2, and then you have to move it one more time, giving us the 20 millijoules right there. So it's really not that difficult, but you do have to start from the beginning, and this is probably the most important equation that you really have to understand and sort of make sure that you know how to write that down. And also know that the stored charge in here is the same as the stored charge in here. That was something we covered right at the beginning of capacitors. When you know all that, you can solve the equation for all of the charges. Then it's a matter of using the general equation for capacitance to find the voltage, and you can always kind of double check your voltages to see if they make sense, which we did, and then take all of that information and calculate the stored charge. I'm Jason. I hope you've learned something in this section. We've covered a lot of material. The main thing to really realize is that a capacitor contains an electric field inside of it, and because of that, it has the potential to do work. How does that potential to do work come about? Well, it's because you've got a stored charge in there, and that charge can go off into the rest of the circuit whenever you connect it in there, and that's basically what you have. There's an electric field in there that's storing that energy, and that's sort of acting like that energy storage device that we use in circuits. So that's what we need to understand. And the energy of an electric field in free space we talked about also. You don't have to have a capacitor to store electric potential or potential energy. The fact that an electric field is even in the room is enough for energy density to be in this room. And it's kind of hard to believe at first because, it's invisible. You can't see it. You can't see an electric field just if a field is right in front of you. You can't see it. Doesn't have any touch or taste or anything, but it does have potential energy, potential to do work. So we say it has energy stored associated with that. So when you build a capacitor that has these plates and these charges that basically generate an electric field inside, well, there's going to be energy stored inside that capacitor, and that's what this whole section's been about. I hope that you've learned something, practice your problems, understand the definitions of things, and you'll be one step closer to understanding all the little details of electricity and magnetism.